Now let's talk about rock structures formed by brittle deformation. The most important example is going to be the faults. Faults are the fractures in rock, and that fractures are going to be actually creating the surface which displacement has occurred. The sudden movements along faults are the causes of the most earthquakes. When we look at the geometry of a fault structure, we will see that a fracture surface where the actual brittle deformation occurs, and then we will have both sides of that rock body called either hanging wall block or footwall block. So here we will talk about different types of faults. First one is normal fault. In this case, we will have tensional stress. So we'll be pulling the rock body from both sides away from its center. In this case, the fracturing is going to occur somewhere in here, and one side of that rock body is going to move downward, while the other side stays at its original position. And we call this moving downward side as hanging wall block, and the side stays in its original position as footwall block. Normal faulting mechanism actually can lead to some really interesting structures, which we call either as graben or horst. When we have two normal faults acting towards each other, so the area in between them is going to be the area moving downward, we call this entire area as graben. So the low areas in between two normal faults are going to be called as graben. And when we have two normal faults acting in different directions, so the right side of this fault is going to go down and left side of this fault is going to go down. The part stays in the middle of them as high is going to be called as horst. The second type of fault is the reverse faults. In this case, we have compressional stress. So both sides of the rock body will get pushing stresses towards its center. And by this stress, this differential stress, one side of the rock body will move upward along this fractured surface, while the other side stays where it is. In this case, this moving side, we will call as hanging wall block, and the other side staying as where it is will be called as footwall block. There's another type of fault which actually is exactly the same thing with reverse fault, except the directionality angle of this slope on the fracture surface. So again, we have compressional stress. Again, we have hanging wall block moving upward and footwall block staying as its original position. But this fractured surfaces slope is going to be steeper than 45 degrees. And this type of reverse faults, we call them specifically as thrust faults. Another type of fault is the strike slip. In this case, we don't have tensional or compressional stress, but we have shear stresses. So we will have stresses coming from two different directions on both sides of the fracture surface. The fracture surface is right here in the middle, and this right block will be pushed up here in this direction, and the left block is going to be pushed down here in this direction. When we stand on one side of these blocks, one side of this fractured surface, and look at the other side, if that side across the fractured surface moves towards left, we call this as left-sided strike slip fault. And if it moves towards right, we call it as right-sided strike slip fault. There is another type of rock structure formed by brittle deformation, which is called as joints. In this case, the rock gets fractured, but there won't be any movement. And most joints will appear in parallel groups as we see in this picture. Now let's briefly talk about mountain building. Here you see the world map with different locations, different types of mountain belts. This brownish color you see along South America, North America, and in here from Europe all the way to Asia. These are the young mountain belts. And the purple ones are the oldest ones that we know on Earth. Yellow parts are usually inland, are away from boundaries of tectonic plates, but they are high. We call those as shields. There won't be much rock movement going on in those areas. And then we have these gray areas. These are older compared to these shields, and they are more stable and actually covered by sedimentary rocks. Now let's look into a few different types of mountain building. So there is collisional mountain belts. In this case, we have two plates moving towards each other. Continental plate over here, since it's denser, will move underneath and subdike underneath the continental crust. And like happened with India and Asia, the entire oceanic crust is actually consumed by this movement, and then it keeps going with both continental crusts of Asia and India. This movement will lead to upward movement of this material accumulated in here. So it is here forming Himalayas in between India and Asian plates. Another type of mountain building is going to be by Cordilleran type mountain belts. In this case, we have a few different structures, such as an inactive island arc formed by a hotspot. And then we may have a microcontinent, which is going to be a form of land in an ocean. And again, we have this oceanic crust subducting underneath continental crust. First, there will be these islands head to continental crust and spend in between these movements, in between these two plates. Later, the microcontinent will come, and that also will go through the same process. And all this material accumulated in here will be pushed upward by the subducting movement and then create a mountain belt over here. Another type of mountain building can be Andean type. In this case, we have this accretionary wedge, material accumulated by the movement of the subducting lithosphere. It is carrying material and depositing them along this trench. And on this side, we have Pluton coming up because of the subduction, carrying water, having rocks being able to melt in lower temperatures because of the existence of water. All this melted material will move upward due to its buoyancy and lower densities and form this plutons or batholith, which is an intrusive igneous structure, igneous rock. And this continuous movement of this subduction will keep pushing this material upward. And since it's igneous, it is going to be quite hard to erode this material. So it is going to get exposed and stay there as a high area and form a mountain belt. The last thing I would like to talk about is isostasy. So when we think about a series of different sized blocks floating on water, we will imagine that parts of those blocks are going to be above the water and parts of them are going to be below the water. And this distance, this ratios between the parts being above and below the water is going to be defined by the density and size of these blocks. Same thing happens with mountains. So sometimes we have this top parts of mountains and the roots of mountains are acting following this isostasy. It is actually a very common thing. So in this case, gravitational forces are balancing the actual mass of the mountain range we are talking about. Here there's a more realistic example, something that we can observe in the nature. So here, compressional stress going on. So the oceanic crust moves towards continental crust, and by this compressional stress from both sides of the body, we will have thickening in the middle and shortening along the stress direction. And this thickening material means we will have more thick and heavier stuff accumulated in here. This actually will lead to isostasy happening, and then the root of this mountain will get deeper. And in this case, this movement will push mantle towards the sides, and we'll have this nice shape of deep root. In time, we will get erosion. Once we get erosion, that will mean that we will be removing material from here. So the weight is going to get less. And that less weight is actually lead to uplift, because now the root doesn't have to be this steep to balance the entire material sitting on top of mantle. And this upward movement, isostatic uplift, will allow mantle flowing back to its original position underneath the root of this mountain. When we have even more time passed by, there'll be more material will be removed by erosion, and this uplift will keep continuing. And at some point, the mantle will flow back to its original position, and we will have this continental crust being quite uniform on top of it and at the bottom and the root of it. So here there's another example, another figure showing the principle of isostasy. Here we have compression. It will be causing the shortening in this direction and thickening in this direction. So part of the material will be looking, going upward. However, due to its weight, the mass, part of it is going to go down. So it's going to create this root. And in time, we will have some collapse due to this stretch and thinning of the crust because of the uplift created by this isostasy itself. And that uplift will actually lead to ductile spreading on both sides of this structure, and we will get subsidence more in the middle, and the height of this mountain is going to get lower. This way we actually can stop the mountains from getting higher and higher continuously. Obviously, they will actually observe those rules of balance coming from the principles of isostasy. That will be it for this subject, and I wish you all good luck for the midterm coming up.